Okay, so in general, the following generation technologies don't really contribute significantly to the overall generation mixture of the United States. They may have other advantageous applications, so we're just going to kind of breeze through a bunch of other generation types that you probably don't see very often, but that do exist out there in one-off or two-off applications. The first that we're going to look at is concentrated solar power, or solar thermal power. In a solar thermal system, mirrors or other reflectors concentrate the rays of the sun to heat a liquid or a molten salt. The heat from the working fluid, that liquid or molten salt, is then used to drive a heat engine, most typically to boil water to drive a steam turbine. In these heat engines, the atmosphere is going to provide the low temperature sink, while the high temperature source is provided by solar concentration. CSP technologies perform concentration via three main technologies: linear solar trough technologies, parabolic dish systems with Stirling engines, and heliostats that reflect sunlight onto a power tower. In a solar trough system, the concentrator is made of multiple mirrors that kind of approximate a parabolic shape. The trough will usually tilt to track the sun, and it's going to focus the light energy onto a thermal receiver. That's this tube with a working fluid in it. The thermal receiver tube is filled with a fluid that absorbs the solar energy and therefore converts it into heat stored in the working fluid. The heat from the working fluid is then used to create steam inside of a heat exchanger, and the steam is then used to drive a turbine. Most utility scale solar thermal in the United States is parabolic trough, with the solar energy generating system in California currently producing about 350 megawatts of power in the Mojave Desert. So there's about one big solar thermal technology in there in the United States using a linear trough system. In a dish Stirling system, a giant standalone parabolic reflector is going to concentrate light onto a receiver, which is positioned at the focal point of this reflector. Typically, the reflector is capable of tracking the sun. This whole thing is moving. A working fluid in this receiver is typically heated up to an extremely high temperature, usually about 700 degrees Celsius, and a Stirling engine is used to generate power there. The world record for solar electric power efficiency is actually held by a design of this nature. It's at 31.25%, converting solar energy into electric power. A solar power tower uses heliostats, which are flat movable mirrors, to focus the sun rays on this big collector tower. The collector tower contains a working fluid, which is typically a molten salt, which is used in a heat exchanger to boil water and to drive a turbine. The major advantage of the solar power tower is that due to the energy storage capabilities and high temperature of the molten salt and large volumes of molten salt inside the tower, solar power towers can produce electricity even after the sun has stopped shining. So these are actually used in utility scale. That's its major claim to fame. This guy holds the record, 31.25% solar efficiency. This guy, however, for a number of hours after the sun has stopped shining, there still is stored heat inside the thermal mass inside of this power tower, which you can still use to boil water. So this guy can produce power even when the sun isn't shining. It can help flatten out some of the effects of intermittency of the solar resource. The next technology that we're going to talk about is called a fuel cell. A fuel cell converts chemical energy from a fuel into electricity through a chemical reaction with an oxidizing agent. It's important to note that a fuel cell doesn't utilize combustion, and there are no thermal processes going on inside here. Nothing is burning, nothing is exploding, right? Although there are many different designs, fuel cells all operate on a similar principle. What happens is that we've got hydrogen fuel that's channeled through plates on one side of the fuel cell, and oxygen is channeled through plates on the opposite side of the fuel cell. The hydrogen side here is called the anode, and the oxygen side here is called the cathode. At the anode, some sort of catalyst causes the hydrogen to become ionized, which means it's split into positive hydrogen ions, which in this case is just a proton, and a negative electron. Right? A hydrogen atom is just one proton and one electron, so we get these hydrogen ions that are a proton and an electron. we've got a special membrane in between in here. It's called the polymer electrolyte membrane. It allows only positively charged ions to move across this membrane barrier. And so positively charged ions are going to pass through and into the cathode. Negatively charged ions are therefore going to build up on the anode of the device. Right? We get this polymer pulling off these protons, putting them onto the cathode. We've got a buildup of electric charge on the anode. The negatively charged electrons can only escape the anode if they travel alongside an external path, an electric circuit. And this is how a fuel cell provides current. At the cathode, these electrons are going to recombine with the oxygen and in here and the hydrogen, and they form water, which is going to flow out of the cell. Most of these little fuel cells produce about 1.16 volts, and like solar cells, fuel cells have to be assembled into larger units. In this case, they're called fuel cell stacks. The output voltage, current, and power of the fuel cell stack is going to depend on the number and size of the individual fuel cells comprising the stack, and also on the geometry of the fuel cell itself. The next technology is biofuels. So biofuels are derived from either biomass or bio-waste. Although typically used in the transportation sector, they have found applications to produce electric power. Unlike transportation fuels, biofuels used in the production of electricity are typically solid. The preference for solid biofuels in power generation is derived mainly from the fact that it's easier to store than liquid fuel, which needs to be stored in tanks. Solid fuels can just be stored in big piles on the ground most of the time. Because the fuel needs to only be transported to the site where it's burned, mobility is not a major consideration like it is with some of the liquid fuels. Power generation facilities are pretty tolerant of contaminants, debris, and other imperfections that would rather render biofuels useless for more typical transportation applications. So the biomass that is used to produce electric power doesn't really have to be pure or really have that consistent of a quality. And that means biomass used for power generation can be extremely inexpensive, and this kind of drives the cost of producing electricity from biofuel down. However, this isn't used a whole lot unless there is a glut of biomass material. Why? Well, while it might be true that fuels could offer benefits in power generation, these fuels are pretty generally offset by the high costs of production, right? So usually what you see is these biomass power plants being located in facilities that produce waste products that can then be reused to make plants more efficient. For instance, a factory might produce paper and they've got waste products that can be then burnt after producing the paper to produce electricity. It produces electricity, which is a benefit. It reduces waste disposal costs, it reduces electricity costs. Usually it also produces processing heat, so it reduces heat costs. So long term, though, you're probably not going to see a major influence in biofuels in the electrical generation market for two major reasons. First of all is using waste biomass is typically a means of ridding agricultural of waste, and is very inexpensive. But this is a world of difference from growing crops specifically to burn in power plants. So large-scale adoption of this, where we actually grow fuels to power power plants, is probably not ever going to be an economical method to produce power. It'll probably just be relegated to situations where we're trying to burn waste products from other situations. Beyond monetary concerns, biomass also does pollute. With the need to cut down on greenhouse gas emissions, electricity generating industries really have been a prime focus on carbon reductions, right? As we've talked about a little bit. Burning these biofuels emits greenhouse gas reductions, or emits greenhouse gases. So we do have kind of an incentive to utilize other green technologies other than the biofuels. So they don't get a whole lot of attention because of that reason. We're going to look next at technology because of geothermal. In a geothermal power plant, steam is produced from reservoirs of hot water that are typically found a few miles or more below the Earth's surface to produce electricity. This steam will rotate a turbine that activates a generator to produce electricity, as we've seen multiple times now. There are basically three types of geothermal power plants: dry steam, flash steam, and what's called a binary cycle plant. A binary cycle power plant draws steam from an underground steam reservoir. This is steam that exists in the earth. The steam is piped directly from underground wells to the power plant. It comes up through this turbine. It spins a turbine kind of directly, right? Where then goes into a condenser and then can be piped back down into the steam reservoir. Right. There are only two known underground resources of steam in the entire United States. These are the geysers in Northern California and also in Yellowstone National Park in Wyoming, where Old Faithful is located. Yellowstone, clearly there is not a power plant at Old Faithful, so we only in the United States have one power plant. It's operating at the geysers in Northern California. It uses this dry steam geothermal technology. It extracts steam from the earth, uses it to spin a turbine. But again, one place in the entire United States where that is done. Flash steam power plants are much more common, and what they use are geothermal reservoirs of water that have high temperatures greater than 360 degrees Fahrenheit. So we've got this geothermal zone in the earth where there's just hot water. It's not steam, it's just hot water. And so we pipe into that. This very hot water flows up through wells that have been tapped into the ground under its own pressure. As it flows upward, pressure decreases and some of the hot water then flashes into steam. The steam is then separated from the water here, and then it's directed into a turbine, which again is connected to a generator that goes into our typical typical condenser unit that we see here. Any leftover water is condensed in the condenser unit, and then, or if it's steam, it's then cooled and condensed. This brine is then combined. We may have some direct heat uses from that, but typically what happens is that we just inject all that back into the well, so it's a closed flash steam system. So it's called flash steam because as the pressure decreases, this hot water flashes into steam at some low pressure, and we use that steam to turn the turbine. The last cycles, the binary cycle power plants, these operate on water that's got even lower temperatures, 225 to 360 degrees. So, not hot enough for these flash steam geothermal plants. So we've got this hot water. It flows up from wells in the ground, and you can see what it is that we use it in a heat exchanger. Right? As the pressure decreases, we've got kind of a water going through here. It then comes in contact with a working fluid inside this heat exchanger. The working fluid's vaporized, typically inside this heat exchanger. It's then used to spin a turbine. In this case, you're seeing isobutane as the working fluid. It then is condensed back into a liquid inside the condenser and goes through this kind of closed loop system. The water or the hot brine that's coming from the ground is then, after it runs through the heat exchanger, it's then injected back into the ground. And the ground, it then absorbs the heat energy from the earth, and it can recycle that usage. The water and the working fluid during this are kept separate during the whole process, so there's little to no pollutions indicated in those. So the next technologies we're going to look at are ocean-generated electricity, and this is the capturing of energy in tides and waves, and then a third very uncommon technology called ocean thermal energy conversion. And we use these, basically, we use ocean thermal to produce heat, or produce electricity from the heat stored in the ocean depths. Currently in the United States, there is no tidal, there are no wave power plants, there is no ocean thermal. These are just technologies that are operating elsewhere in the United States or are being currently developed. So this is kind of the newest cutting edge. However, the geographical features of both the Pacific Northwest and the Atlantic Northeast coast offer really great conditions for making tidal and wave power. This this ocean thermal technology works better in warm water, such as off the coast of Hawaii and South Florida. So although these aren't being used currently, they do have some future applications. So first, let's talk about tidal. Tidal power can be converted into electricity in 3 ways. The first is that we've got a barrage or a dam, and what happens is we've got seawater that gets forced through a submersed turbine. So we somehow channel the water from the tidal flow. As the flow, basically what will happen is we have a basin, it fills with water at high tide. When the tide goes out, we force that water through a different channel, it flows past a turbine, right? So there's a dam structure here that stores water and then releases it. So it captures the water during high tide, releases it during low tide, letting it spin past this turbine. The key being that we control the rate at which that flows due to this basin, right? Tidal fences, these are basically giant turnstiles. You got a generator on the bottom. This basically operates like a wind turbine, right? There's a vertical axis turbine here. It gets spun as water passes through it. As the tide goes in, it spins in one direction. As the tide goes out, it spins in the direction, spinning this generator on the top of it. Probably receiving the most attention are tidal turbines. These are basically wind turbines underwater. So they're located in about 65 to 100 feet deep, and as ocean currents flow past them, they turn a propeller and they generate electricity. So we've got a couple ways to capture wave energy. Offshore systems have typically been placed in water way further out than the tidal. So, tidal are kind of close to the coast. Wave systems are kind of far away from the coast, usually in water depths are about 125 feet deep or greater, and they also have 3 methods. The first is called the Edinburgh duck, and basically what happens is as waves move back and forth, a pump goes up and down under the motion of the wave. The next is that we've got floating hoses. We have hoses, pressurized water then flows through these hoses, and turns a turbine. And then finally we've got floating platforms. These platforms funnel waves through internal turbines and back to sea. So that's what this picture is we got this floating platform. Waves will flow through it, turn a turbine, and then go back out the other side. None of these are particularly common. The Edinburgh duck as pumps or generators move up and down. That's probably the most common when it comes to wave systems. Onshore wave systems, as opposed to these kind of like deep water technologies, are typically built closer to shorelines, and they have a couple technologies. One's called an oscillating water column. Basically, you've got a column of air that's enclosed above a column of water. As the water flows through the column, it compresses the air and then drives some sort of mechanical system. We've got what's called a tap chin. We can increase the wave height by moving water through a narrowed channel. So we artificially push the wave, constrict the wave's motion through a narrow channel, causing it to go higher than it normally would. And finally, we've got something called a pendular, which is a pendulum device that runs on a hydraulic pump and generator. Very, very uncommon systems, but kind of in development. Finally, the last technology for ocean is ocean thermal systems, and these conversion technologies create electricity via either open or closed loop thermal systems. So in a closed cycle system, what's happened is that warm surface seawater is pumped through a heat exchanger, which is used to vaporize an extremely low boiling point fluid, such as ammonia. That vaporized fluid then turns a generator. Cold deep seawater is pumped through a second exchanger, which condenses the vapor back into a liquid and then allows that cycle to continue. Open cycle systems boil warm surface seawater to create steam that turns a low pressure turbine. Steam is then the water steam is then turned back to a liquid by exposing it to the cold temperatures from the deep ocean water. So basically just big old heat exchangers. And that is really a summary of all the power generation technologies that exist out there. So that's the end of module 4.4.